Hi everyone, thanks for coming to my talk and thanks to the organizers for putting together this conference. My name is Paula and I'm a PhD student at Queen Mary University of London, and today I'm going to be talking to you about some work I've been doing on cosmological parameter estimation with 21 centimeter intensity mapping with these collaborators. So first, an outline of my talk. I'm going to start by giving some motivation as to why we look at 21 centimeter intensity mapping, and then I'm going to talk about how we can model the 21 centimeter intensity mapping power spectrum, including instrumental and systematic effects. I'm also going to compare this modeling to some simulated data, which includes these effects. And then I'm going to talk about the covariance matrix and how to model the uncertainty in the 21 centimeter intensity mapping power spectrum. And finally, I'm going to bring all of this together and show some parameter estimation results. So first, why intensity mapping? So intensity mapping measures the intensity and redshift of the neutral hydrogen, or H1, 21 centimeter line across the sky. It does not try to detect neutral hydrogen inside individual galaxies, because that would be too costly, but instead it treats H1 as just a diffuse background, which means it can scan large volumes of the sky very quickly. And because after reionization, most of the neutral hydrogen in the universe can be found inside self-shielding galaxies, this means that H1 is a really good bias tracer for the underlying matter distribution of the universe. And so we can use H1 to map the three-dimensional large-scale structure of the universe. So let's talk about what is the simplest model we can have for the H1 power spectrum. So the simplest model is an isotropic model, meaning it's only a function of the inverse length or inverse physical separation K. And this model is just a combination of the underlying matter power spectrum combined with the H1 bias, because it's a bias tracer, and also the H1 background temperature, because what we're actually measuring is fluctuations from this mean H1 background temperature. And this is proportional to the cosmic density of H1. But what we actually measure is the anisotropic power spectrum, meaning it's a function of K, but also mu, which is the angle between K and the line of sight of the observer. So this means that the H1 power spectrum is an isotropic, and it's actually dependent on where exactly we look in the sky. And why is this? So this is because of redshift space distortions, or RSDs. And RSDs come about because we're measuring fluctuations in redshift space, but objects have peculiar motion, which means that the observed position of them gets distorted along the line of sight because of Doppler effects. But RSDs are important because modeling them allows us to probe interesting cosmological parameters such as F, which is the growth rate of structure. And we also have other effects such as the Alcock-Paczynski effect, or AP effect. And this effect comes about because we are measuring in redshift space and then we are converting to a distance. But to convert from redshift to distance, we have to assume a cosmology. And if this assumed cosmology is different from the actual underlying cosmology of our universe, then we're actually going to have some distortions in our measurements. So along the line of sight, we're going to have distortions in the Hubble parameter, and in the direction transverse to the line of sight, we're going to have distortions in the angular diameter distance parameter. And these parameters, alpha parallel and alpha perpendicular, allow us to then try and measure these distortions. So they're really interesting cosmological parameters. And we also have in this model sigma v, which is the velocity dispersion of the objects, and the shot noise, which comes about because we're trying to probe a continuous field, an overdensity field, using discrete objects. And so these are the 6 parameters in our model, and the most important ones that we're interested in are the first 4. So the 2 AP effect parameters, the growth rate of structure, and the H1 bias. A useful analysis tool for looking at the anisotropic power spectrum is multipole expansion. So multipole expansion allows us to decompose the power spectrum into multipoles using Legendre polynomials, which are a set of orthogonal polynomials. And we look at the L equals 0, 2, and 4 Legendre polynomials, and going beyond 4, things get very nonlinear, so we stop there. Let's also talk about how we can simulate single-dish H1 intensity mapping. So first, we take an n-body simulation. So we use the multi-dark simulation at a redshift of z equals 0.82 with a box with sides of 1 gigaparsec per side. And this simulation actually has a cold gas mass for each galaxy, and we can map the cold gas mass to H1 mass, and then smooth this field with a large telescope beam, which we can expect from a futuristic intensity mapping survey such as the SKA. So let's talk about the telescope beam. So the telescope beam actually determines the resolution of our survey. So we can actually discern structure that is smaller than the telescope beam, meaning that anything smaller than the telescope beam is going to get damped. So the telescope beam damps power on small scales. And here you can see, for example, just an overdensity field without the telescope beam, and then with the telescope beam, you can see that you're really losing a lot of resolution. And we can model this as just a Gaussian damping function, which damps these small physical scales as a function of the size of the beam. And this beam actually acts only along the perpendicular to the line of sight, so it adds even further anisotropies to the power spectrum. Here we can show just the agreement between our model and the simulation for the monopole, quadrupole, and hexadecapole multipoles. And we can see here that our model seems to agree well with the simulations. Let's also talk about systematic effects. So when we actually try to measure this H1 signal, we actually also end up measuring a lot of foregrounds that are up to 5 orders of magnitude or larger than our actual H1 signal. So our H1 signal gets drowned out by these huge foregrounds that we're also observing in the same frequencies. And most of these are synchrotron emission coming from our own galaxy. So how can we then try and remove these foregrounds? Well, we can differentiate the foregrounds from our signal because the foregrounds are actually smooth in frequency or redshift. So they're smooth along the line of sight, whereas our signal isn't smooth because it's tracing structure. And we can use lots of different methods to try and then remove these foregrounds. The one we use is something called independent component analysis, which basically differentiates the foregrounds from the signal by looking at them being statistically independent from each other. So basically what this means is that it's finding the foregrounds because they're spectrally smooth in frequency and the signal is not, and then it's removing the foregrounds. But we do have some effects from this foreground clean. So when we actually perform this foreground clean, the largest fluctuations that we have in our box of simulation or survey also appear smooth along the line of sight. And so these are going to get confused with the foregrounds, and they're also going to be removed. And so we are going to lose power on large physical scales. And our power is going to be damped. As you can see here, at the top we have just an intensity mapping simulation without any foregrounds. And if we then add simulated foregrounds and remove simulated foregrounds from this, you can see at the bottom, power is clearly being damped. And here as well, you can see just in terms of the power spectrum, when we measure the power spectrum of this foreground cleaned case, you can see it's really being damped on large physical scales. And our model doesn't seem to fit it well anymore. But we can actually try and model the effects of foreground removal in the same way that we try and model the effects of the beam. So with the beam, we actually model it as a Gaussian damping function, which damps scales in accordance to the size of the beam. And with the foreground, we can also model it as a Gaussian damping function, which now damps large scales as a function of the actual size of the box. So this is because the size of the box determines which scales are actually getting confused with the foreground and removed. So that's why we have here the largest scales you can fit in the parallel and perpendicular directions of the box. But we also have these parameters n perpendicular and n parallel, which determine how much of these scales is being damped. So if n parallel and n perpendicular are bigger, that means a lot of power is being damped. And we find, just with a simple fit, that the best fitting values for these parameters are n perpendicular equals 2 and n parallel equals 2. And you can see here now that if we include this foreground damping model, that our model fits the data, the foreground removed data, actually quite well. So let's think a little bit further about why exactly n perpendicular equals 2 and n parallel equals 2. So it's easier to think about it in terms of the line of sight direction. So here we just have our simulation box, and where the x-axis is just a line of sight direction, so redshift or frequency. And at the top curve is just the smooth foreground. And then the second curve is the largest H1 sigma fluctuation you can fit inside the box. And this is determined by K parallel min and the size of the box. And this is obviously going to get confused with the foreground because it appears smooth. But the fact that we get n parallel equals 2 is telling us that the threshold for being able to differentiate our signal from the foreground seems to be half of the largest fluctuations we can fit in the box. So that's this third curve here, is half of the largest fluctuations. And you can see here you have 2 fluctuations which fit inside the box. And this is clearly not smooth. But when you can only fit 1 fluctuation, this appears smooth. So the n parallel equals 2 limit actually makes some physical sense. Let's also talk about the uncertainty in this power spectrum. So here we just have the Gaussian covariance between k and mu bins, where you have the H power spectrum model, which is just the sample variance, and then you have Pn is just the instrumental noise from your survey, and we're here simulating an SKA-like survey. And also you have the number of modes you can fit in each k mu bin. And so this, because we have the H power spectrum model here, this is the uncertainties are going to be affected by the beam and the foreground removal effects. So we include these, and we also don't ignore the covariance between different multipoles. And this is because when you actually look at the correlation matrix, you can see if we ignore the beam and if we ignore foregrounds, then the different multiples here don't appear super correlated, especially the monopole and the hexadecapole. They don't appear to be super correlated. But in this bottom panel here, if you look at the correlation function, when we include the effects of the beam and when we include the effects of foreground removal, you can see that things appear much more correlated. And because of this, we actually include the covariance between each multipole with themselves, but also between each different multipole with each other. But more work is actually required in order to fully understand this and actually measure the covariance matrix of foreground removed data with lots of simulations. But this is just an interesting starting point. So now let's combine all of that and try and run some parameter estimation. So first we look at the foreground free case and we run an MCMC analysis using our simulated data and our model and our covariance matrix. And we find that we can get unbiased results for our cosmological parameters, meaning that we get back the actual fiducial cosmology of the simulation itself. So our model is good enough in this case. And so you can see when we just include the monopole and the quadrupole, where most of the information is, we do get good constraints on the parameters, but when we include the hexadecapole at a restricted range, because it's more nonlinear, we get even better constraints on our parameters. So even if we're only adding the hexadecapole at a smaller k range, because otherwise results become biased, because things are more nonlinear there, we can still get improvements on our uncertainties on our cosmological parameters. You can see we actually get fractional uncertainties below 10% for the 4 cosmological parameters of interest in our case, when we include the hexadecapole. So now let's look at the foreground removed case. So in the foreground removed case, we first take foreground removed data and try and fit our foreground free model to it, which we saw was not a good fit. And as expected, we actually get back biased cosmological parameter results, meaning definitely the model is not good enough to fit the foreground removed data. And that's just this orange dashed line here. You can see the results for the parameters are biased. But then we take our foreground model and then we try and fit our foreground removed data using our model with the foreground damping effect. And we can do this either by fixing n perpendicular and n parallel to be 2, which we found to be the best fit just by eye, or we can let them vary. And obviously we get smaller uncertainties if we keep n perpendicular and n parallel fixed, because then you don't have more free parameters. But this is unrealistic because you wouldn't really know these parameters perfectly beforehand in the case of real data. So what we do is we let n perpendicular and n parallel vary. And here you can see, again, we first include just the monopole and the quadrupole, and then we include the hexadecapole at a restricted range. And when we include the hexadecapole, we do also get good results on the uncertainties of our parameters, but the uncertainties are actually larger now because we have 2 extra free parameters. But the most important thing here is that we can get back unbiased parameter results when we include our foreground model. And yeah, it would be interesting to keep checking this foreground model on different simulations or more complicated foregrounds and see what we get. So as a summary, we've shown that we can model the effects of the telescope beam and foreground removal effects for a future H1 intensity mapping single dish experiment. And we've shown that this modeling agrees well with simulated data. We've also shown that these instrumental and systematic effects make the different H1 power spectrum multipoles more correlated, but more research is required to fully understand this effect on the covariance matrix, for example, by taking lots and lots of simulations and actually measuring the covariance matrix in the case of foreground removal. We've also shown that in the absence of foregrounds, we can use our modeling to obtain unbiased cosmological parameter results and uncertainties, fractional uncertainties below 10%. And then in the presence of foregrounds, that model isn't good enough anymore, but we can use our foreground model to obtain unbiased parameter results just with slightly larger uncertainties. Thank you very much.